Uh, so thank you so much for the invitation and the opportunity to be here. The work that I'm presenting is, it's under revision at the moment, but it should be appearing in the next few months, we hope. It's joint work with Dave Yan and Francis Dawson. Francis Dawson is an electrical engineering professor, and Dave Yan is a student that we had together. The talk is going to try to be as user-friendly to people who are not numerically literate, and it's sort of an analyst's approach to these questions. So there's a roadmap, but rather than reading through a table of contents, you can see it. The goal of this talk is, this is the stability region for a numerical scheme. And when you open when you open numerical analysis books and you look at stability domains, you don't usually see, right here, there's actually a corner, and there's a corner, and there's a jump. Obviously there's a jump. And both of these are not the types of things that you see in generic articles. You certainly don't see them in graduate textbooks. And the puzzle of this talk is, where did these come from? Why did they happen? And so before we get to this, I'd like to just warm up. So let me remind you, so if you have a system of ODEs with initial conditions, so here this is just a generic initial value problem, then if you wanted to put this on a computer, what you would do is you would find a sequence of values, a sequence of vectors in Rn. U0 would be the initial data, and U1 would be approximately U at time delta t, and U2 would be approximately U at time 2 delta t, and so forth. And so what you would be doing is, rather than constructing the solution, which is a continuous curve, you would be trying to find a sequence of values which are close to the curve. And the smaller the dt is, the closer you get to the curve. And so this is when people numerically approximate a solution to an ODE. What they're doing is they're getting a sequence of points. Those are the reds. And you have the purple is the true solution. And as delta t goes to 0, you get more points and you get closer to the curve. Now, when you teach ODEs, you teach about the stability properties of fixed points of the ODEs. And the way you would understand the stability of a fixed point is you would look at the deviation from the fixed point. So you would take the solution and you subtract the fixed point, and then you would find an equation that the deviations approximately satisfy. And that equation is, you just compute the Jacobian of the vector field, and you compute the Jacobian and you evaluate it at the steady state. You now have a linear system, and if you're lucky, certainly the linear system has a Jordan canonical form, and if all of the eigenvalues have negative real parts, then it's an asymptotically stable steady state. And really, if it's diagonalizable, then you can actually decouple, and you just have to worry about a system of, you just have a system of n ODEs, each ODE of the form U prime equals lambda ku. So this is wonderful. And that's how we study the stability of a system of ODEs around a steady state. You can do the exact same thing for a discrete dynamical system. And so when you approximate the solution of the ODE using a numerical method, really what you're doing is you have a discrete dynamical system. You have something called a time-stepping rule. And what the time-stepping rule does is, given the current value, it gives you a future value. Or given the current and a past value, it gives you the future value. But you have a discrete dynamical system which generates the new value again and again and again. And so, for example, if you're doing something called forward Euler time stepping, this is the one that shows up in calculus books. What you do is you take the current value, you evaluate the vector field at the current value, you multiply by your time step size, and that's how you build the new one. Now, you could just write this as a discrete dynamical system, which has a parameter, dt. Now, to find the stability of a steady state of a discrete dynamical system, you do the same thing that you do with a system of linear equations. You compute the Jacobian about the steady state. You multiply by the time step, and this is the deviation from steady state, the nth deviation from the steady state. And now you have a system of coupled difference equations. So you have n coupled difference equations. And you can, because you have only one Jacobian, you can carry the entire, you can do the Jordan canonical form theorem, and you now have a new system. This is Jordan form. And if you're lucky, it's actually diagonalizable. And you realize that all you're looking at is a system of the form un equals 1 plus dt, the kth eigenvalue of the Jacobian. And so you see whether or not things decay to the steady state. So the point is that if the continuous problem has an asymptotically stable steady state, you would like your numerical simulation to respect the fact that the steady state is asymptotically stable. And so if the continuous system had an asymptotically stable steady state, that means the continuous system, all of those eigenvalues have negative real part. The discrete system, all of the eigenvalues will have magnitude less than 1 if you take a small enough time step. And so one point is, if the steady state of the continuous problem is asymptotically stable, you would like your numerical scheme to have an asymptotically stable steady state. The other point is, if the Jacobian diagonalizes, again, we've decoupled the entire problem into a system of difference equations, decoupled difference equations. And then all you need to do is understand, how does the numerical scheme perform on a single ODE? So again, the idea is that if the Jacobian diagonalizes, then you just need to understand how the time stepper works on one ODE instead of having to understand the full system. So language, a time stepping rule is unconditionally stable if when the system of ODEs has an asymptotically stable steady state, then the discrete system will have an asymptotically stable fixed point for every value of dt. And it's conditionally stable if the fixed point is asymptotically stable only for time steps that are small enough. And so we've seen forward Euler time stepping is conditionally stable. But the big point, and this is something which is not in the numerical analysis courses at least the introductory ones, because maybe it's supposed to be obvious, but it isn't that obvious. Whether or not a particular time-stepping scheme is stable depends on the system of ODEs that you're approximating, as well as what the steady state is that's being linearized about, because all of these Jacobians are there. And so it's possible that you could have a scheme which is unconditionally stable for one problem, and the exact same scheme might be conditionally stable for a different problem. And this is the take-home message of today's presentation. If this is all that you get, then I'm happy. I hope you get more. So far I just talked about forward Euler. Now, what forward Euler does is, given a current solution, it generates the next solution. And given that, it generates the next solution. And given that, it generates the next solution. It's very simple and easy to code, but it's not the most accurate thing. And so there are other approaches where you would do something like, given the current solution and a solution which is one step in the past, you would use the two of them to generate the next solution. And then you would use these two to generate the next solution. And then you would use those two to generate the next solution. So this is what's called a multi-step method. And Runge-Kutta is another way of making things more accurate. It's similar to a multi-step method in that you keep using the vector field in the same way. So we're looking at the system du dt equals f of u. And what a multi-step method does is the future value plus a linear combination of current and past values is equal to the time step size times a linear combination of the vector field at current, past, and sometimes future, sometimes one into the future value. And you choose the coefficients a and b in a sensible way. And this gives you a way of generating the future value using the vector field and past values. And a steady state would be a fixed point of this system of difference equations. So this is a multi-step method. A Runge-Kutta method is not hugely different in terms of what I'm about to say. So if you linearize about a fixed point, you look at the deviation, the deviation of the nth iterate from the fixed point. And all of those vector fields become Jacobians. So before we had f, the vector field evaluated at some solution, that has gone to the Jacobian times the deviation. Now, if the Jacobian, if you can diagonalize the Jacobian, so if this diagonalizes, what we have is on the left-hand side, we have a linear combination of vectors. On the right-hand side, we have a linear combination of matrix times vectors. If it's diagonalizable, then you can diagonalize the full system. And so here I've got the, I've transformed things into Jordan canonical form. If things actually diagonalize, then I've gone from a system of n coupled difference equations to one difference equation, n decoupled difference equations. And each difference equation is going to have an eigenvalue, but all I need to do is just understand how the time stepper behaves on this ODE. And so when you learn numerical analysis, the time steppers are always built and tested on this ODE. And it was never clear to me when I was a student, why is this the only ODE we ever care about? Why do we build and test our time steppers on this simple linear ODE when life is more complicated, when life is systems of ODEs? And the answer is that for something like a multi-step method or a Runge-Kutta method, if you're wondering about the stability of a fixed point, then you're just going to diagonalize, you're going to change coordinates, and you're going to have decoupled systems. And this is why people just simply studied this one ODE. Now, there's something which is different from the traditional multi-step or Runge-Kutta approach, and it's something called a semi-implicit method. And what you do is you view the right-hand side as the sum of two terms. And often what happens is you might have one term which is nonlinear, and another term which has fast timescales. But is linear. And so if you can decouple your right-hand side in this way, then what you can do is you can do something which is a semi-implicit method. So this left-hand side, that's approximating du dt. The right-hand side, you have something which is in the present and something which is in the future. And so you need to solve for un plus 1. Now, this is easy to do if G is linear. And the reason these semi-implicit methods were created was because something like forward Euler, it had a requirement that the time step be small. Whereas semi-implicit methods can often avoid that time step constraint because they do the fast time scales implicitly. And so semi-implicit methods are very popular for PDEs that involve diffusive terms, and they're popular for Navier-Stokes and various hyperbolic systems. So this is a semi-implicit method. Now, again, if I have a steady state for the system of ODEs, I would introduce the deviation from the steady state, and I would linearize about the steady state, and I would get that the deviations approximately satisfy this linearized system. But now you see that there are two different matrices. And so if I can simultaneously diagonalize those two matrices, if those two matrices have the same eigenvectors and eigenvalues, then I would be in a situation where I would be looking at dn plus 1 is equal to dn plus dt mu k dn plus dt rho k dn plus 1. So if I could simultaneously diagonalize, then I would have something where I can actually analyze a single difference equation. But if I can't simultaneously diagonalize, then understanding how the time stepper behaves for a single ODE isn't useful. And this means that all of the techniques built up in the numerical analysis books and built up for multi-step methods and Runge-Kutta methods, they don't help understand the stability because I have a system which cannot be diagonalized. And this is something that happens precisely because I'm doing this precisely for semi-implicit methods. All right, so now I'm going to pause and switch the topic for just a moment to adaptive time stepping, because it's going to come in soon. So when you build an adaptive time stepper, what you do is you try to choose the time step size so that the local truncation error is small enough, but not too small. And so you're trying to figure out what is the time step size so that the new solution is accurate, but not too accurate. So you want the time step size to be small enough that you're confident you're accurate, but you don't want the time step size to be so small that you're overly accurate and you're just spending too much time running your program. And so the idea is that you want your local truncation error to be less than one value, tolerance plus range, and greater than another value, tolerance minus range. And so this will be dt not too small, and this will be dt not too large. So an adaptive time stepper, it can find, it's always changing the time step so that you're accurate but not too accurate. And so if you apply an adaptive time stepper to backward Euler, so this is, backward Euler is, it's the opposite of forward Euler. It's completely implicit. So backward Euler would have no stability constraint. So the key thing is that for backward Euler, there's no stability constraint on the time step size. So time steps can get as large as you want without causing any form of instability. And so here I've computed the heat equation using backward Euler and an adaptive time stepper. And I've got three figures. So the first figure, this one right here, this is the logarithm of the local truncation error. And here's time. And you see that there's this Goldilocks zone. There's the dashed lines. And for the beginning of the computation, the local truncation error stays between the dashed lines. The local truncation error isn't too large, it isn't too small, it's between the dashed lines. And then something happens. Now separately, there's this other figure right here, which is the logarithm of the time step size as a function of time. And so you see that as time passes, dt gets bigger and bigger. Until it runs into a ceiling. This is a user set ceiling. So in the computer program, I have a line saying, do not let the time step size be larger than 1. And the moment I say, do not let the time step size get larger than 1, once a time step reaches that ceiling, the control on the local truncation error is turned off. And that's precisely, this time right here is precisely when I leave this envelope. So this is how an adaptive time stepper behaves when it's computing a problem which has a stable steady state. The heat equation, the unforced heat equation, it's got steady states as long as you've got reasonable boundary conditions, and those steady states are universally attracting. Whatever your initial data is, you're going to go to that steady state. And so this is what you would expect. for something where there's a stable steady state and there's no constraint on the time step size. The time stepper just takes bigger and bigger time steps until some user-specified ceiling says stop. Now, I'm going to apply the adaptive time stepper to something which is slightly more complicated than just a linear equation. So this is the logistic equation. You know it from if you've taught ODEs. It's nonlinear, and it has a parameter, and it has two steady states. So it's got 0 is a steady state and 1 is a steady state. And 1 is the asymptotically stable steady state. So if r is greater than 0, then all solutions go to 1 as t goes to infinity. Now, as a test problem, I'm using a time stepper which is like the semi-implicit time stepper I had before, except that it's second order accurate. So it has the future solution is built, it's two-step and it's second order accurate. The future solution is built out of the current solution and a solution 1 in the past. I use part of the right-hand side at the current, part of the right-hand side at the past, and I use part of the right-hand side at the future solution. This is called SBDF2. It's a semi-implicit time stepper. It has very nice stability properties when you apply it to a single ODE, to a single linear ODE. And I'm applying it to the logistic equation. So the linear term of the logistic equation, so the logistic equation has a linear term. That is done in the future. And the logistic equation has a nonlinear term. That is done at the present and in the past. And so this is how you would apply, this is how you could apply this numerical scheme to the logistic equation. So now you say, well, for the continuous problem, 1 is asymptotically stable. So for the discrete problem, is 1 asymptotically stable? And so you linearize this system about 1, and you find that it's asymptotically stable as long as if dt is less than 4 over 7r, then 1 is stable. What does this look like in terms of a numerical simulation? So here I have fixed, I'm taking time steps of fixed size. This is the time step size. So if I take a time step of size 0.56, then the 1,000th iterate is very close to 1. If I take a time step of size 0.565, then the 1,000th iterate is very close to 1. If I take a time step of size 0.55, the 1,000th iterate is very close to 1. But then there's a transition, and if I take a time step size of 0.58, then the 1,000th time step is one or the other of these two. So this is what so here what I'm presenting is I'm presenting a whole bunch of different simulations with a whole bunch of different time step sizes, and for each simulation, I just simply plot the 1,000th iterate, and I see that there's a bifurcation. This dashed line is precisely 4 over 7r when r is equal to 1, because that's what the simulation is. So the time stepper is clearly doing what you would expect. You see that when the time steps get too large, the attractive fixed point, the u equals 1, which is the asymptotically attracting fixed point of the continuous problem, becomes unstable to the numerical method if the time step is too large. If I use the adaptive time stepper on this problem, Here's what happens if I use the adaptive time stepper on the logistic equation. So again, here's a function of time. Here are the time step sizes. So the time step sizes, they grow, and then they level out. Time step sizes level out. Local truncation error, it stays in that Goldilocks zone. At all times, it stays in the Goldilocks zone. It never gets too big, it never gets too small. I can run the simulation for as long as I want, and the local truncation error stays in the Goldilocks zone. Now, this is the thing that is the most striking. Here, what I'm doing is I'm plotting the distance from the steady state. So this is the logarithm of u of t minus the steady state. And it's plotted as a function of time, and initially it begins to decrease. And then it levels out. Now, if it had leveled out at 10 to the minus 14, then I'd be fine. I'd be happy. I'd say, well, I've gotten to my truncation. I've gotten as close to the steady state as I'm going to. I've gotten down to round off. I would be happy. But this isn't round off. It's of the order 10 to the minus 7. So my adaptive time stepper is not allowing my solution to converge to the steady state. And my adaptive time stepper is, the time step sizes are leveling out. And so if you ask, what is this value? What is this thing? It's precisely 4 over 7r, if r is equal to 1. What this means is that the adaptive time stepper, what the adaptive time stepper is doing is it takes larger and larger time steps, but then it focuses in on this one time step. It takes time steps as large as it can, but no larger. If it were to take small time steps, then it would equilibrate and the local truncation error would get too small. If it takes too large time steps, then it loses accuracy. So there's something going on here where the adaptive time stepper is precisely finding the stability threshold. And so with the logistic equation, you can compute the stability threshold. And so you can actually numerically demonstrate that the adaptive time stepper is finding the stability threshold for the logistic equation. So this is interesting. It allows you to use an adaptive time stepper to explore the stability domain of a numerical method, and it also allows you to it gives you some information, but it also tells you that an adaptive time stepper is not what you should use if you're actually trying to compute a fixed point. So if you want to compute the fixed point, what you would do is you would first use an adaptive method to find a time step size. So you would say that you've used the adaptive method to find stability. And then you would use a fixed point method sorry, fixed time step method, just a bit smaller.
But Mary, may I ask a question? What's the
Please do.
impact of diminishing the tolerance here? Do you get the same behavior when you
Yes,
get the tolerance to 0?
Yes, exactly right. So what's interesting is that this level is determined by the tolerance. So if I were to move my Goldilocks zone, so if I were to shift the Goldilocks zone downwards, then I would get closer to the steady state. But this would be unchanged. So by changing the tolerance, I can get closer to the steady state using the state, but I can't ever actually reach there because I always get the limiting time step size.
So, but can you reach machine accuracy?
Only if I stop and use a use a constant time step size.
Okay.
But this is one of the things, like, so if you code with a constant time step size, then you're always like, well, what time step size should I take? Is 0.001 small enough? How about 0.0001? So when you use a fixed time step, there's always this ambiguity of how small is small enough. An adaptive time stepper, it achieves whatever your desired accuracy is, except that in certain situations, it's not going to find the fixed point. So what you can do is you can use the adaptive time stepper to figure out how small is small enough. And once you have that information, you can use a constant time stepper, a constant time stepper with a time step that you're confident about is small enough. Okay. So it's sort of like having both of them handy. And it's not difficult to do because an adaptive time stepper, it's just gift wrapping on the outside of a regular time stepper. So you use the adaptive time stepper, and then once you want to use a regular time stepper, you just turn the adaptivity off. You change one line in your code, and then you have constant time steps. Okay, so this all came up because my student was studying the Poisson-Nernst-Planck equations, and he was using an adaptive time stepper, and he observed this bizarre behavior of the time step sizes thresholding. And I did not expect the time step sizes to threshold because he was using a scheme for which it shouldn't do that. And so this led us into this study of stability of steady states for semi-implicit time steppers. So let me just quickly tell you what the Poisson-Nernst-Planck equations are. It's here we just have two chemical species. So we have two parabolic PDEs. And we have one elliptic PDE. You have a positive species and a negative species, and you have an electric field, and they're moving around in response to the electric field and in response to one another. And because he's an engineer, he was interested in battery modeling, and there were chemical reactions happening on the boundaries. And so the flux of the positive chemical species has to do with the positive chemical species being created or destroyed at the boundary conditions. So there are boundary conditions, there are nasty, nonlinear boundary conditions. And you can, this is a battery model, and so you can either apply a voltage across the battery, or you can apply a current across the battery. So to make things more complicated, sometimes you also need to compute an ODE. in addition to the two parabolic PDEs and the elliptic PDE and the nonlinear boundary conditions. So it has a steady state. And when you linearize about the steady state, it's the exact same story as before, except this time the Jacobians cannot be diagonalized. It's not a theory. It's not a theoretical case of, oh, you know, maybe they can't be diagonalized. They actually cannot be diagonalized. And so we cannot simply study a single, we do not get second order linear difference equations, a single, just isolated decoupled second order linear difference equations. We have a coupled system of second order linear difference equations. A coupled system of second order linear difference equations. It's linear, so we can compute the characteristic roots, but there's nothing we can do by hand. It's all done using a computer. And so here's a picture. So here I have the time step size. And for any one time step size, so I have 364 roots, and I need to know, do any have magnitude greater than 1? If yes, then unstable. And so what I can do is I can vary my dt. And so for each time step size, I can compute those 364 roots. And for these three lines that I've drawn, all of them have magnitude less than 1. So for all three of those lines, the steady state is asymptotically stable. But then you see that at one value, dt star, I now have a characteristic root which has magnitude 1. And this tells me that the steady state is unstable if dt is greater than dt star. But this is something that, this picture right here is specific to the particular value of, it's specific to the PNP FBD system. It's specific to the particular voltage I had. It's specific to the particular physical parameters I had. But when I've computed all that, when I fixed all that, I can determine when is this, for what values of dt is the system stable. And I can find that. And so now what I can do is I can ask, how does this stability threshold, which I found using the linearization, depend on the singular perturbation parameter, which is one of the key parameters in the problem. So here I've got this perturbation parameter, and the red line, the purple line is dt star, which is the thing I get using the linearization and computing all the eigenvectors, computing all of the eigenvalues, finding the eigenvalue of maximum magnitude, increasing dt until I get one of those branches crossing the unit circle. But separately, I could have just used, what if I just use the adaptive time stepper? In this case, dt levels out at some value, which I can denote dt infinity. And those are denoted with open circles. So what this figure demonstrates is that either I can do lots and lots and lots of work, linearizing the system, computing all the eigenvectors, computing all the eigenvalues, finding the maximum, finding the spectral radius, varying dt, finding a new spectral radius. That's a lot of work. Or I can just compute a single initial value problem using the adaptive time stepper. And you see that the circles align with the solid line quite well. So this is one of the charms of the adaptive time stepper. Now, let me talk about, there's a corner and there's a jump. So right here, there's a jump. So why is there a jump? So the jump occurs approximately at a certain value of epsilon. And so what I can do is I can look at the eigenvalues for an epsilon which is slightly smaller than that, and for an epsilon which is slightly larger than that. And so this is for epsilon just a little bit smaller than the critical epsilon. And what we're seeing is this is a real eigenvalue, and this is a real eigenvalue. And at a particular value of dt, they join and they become a pair of complex conjugate eigenvalues. And that pair of complex conjugate eigenvalues crosses the unit circle at this value of dt. Now, for a slightly larger value of epsilon, I still have, this is a real eigenvalue, and this is a real eigenvalue. And they join and become a pair of complex conjugate eigenvalues. But the instability is right here. And so it's sort of like you've got a narwhal, and the trunk of the narwhal is breaching the surface in the upper plot. But then as the narwhal's head gets closer, it's the narwhal's head which is breaching the surface. And so this is why there's a jump, because there are these two branches. With the corner, you have two branches, and they're competing with each other, and there's one branch and a second branch, and where they cross is the green one crosses first, but then for a slightly larger value of epsilon, the green one is here, and the blue one is here. And so because you have this system that doesn't decouple, you can get these, the loss of stability being due to different branches of the eigenvalues. And so let me deliver the take-home messages, and then I can show you a short little video. So the point, what are the take-home messages? The first take-home message is that you can have a numerical scheme that looks like it's unconditionally stable, and it might be unconditionally stable for a really simple problem, but then when you apply it to a problem that you actually care about, you find out that it's actually, that there are stability constraints. Another take-home message is that you can use an adaptive time stepper as a way of exploring a stability domain. There's separate stuff that we did on using Richardson extrapolation that I'm happy to talk with anyone who cares about. And the adaptive time stepper is wonderful, but the moment you actually want to know what the eigenvectors look like, you have to compute the linearization. So let me show a quick video, just because it's kind of cool. So this is a video of the eigenvalues as epsilon varies. And it's just kind of fun to watch. And so you can see how different branches cross at different times. Here the narwhal is about to come up and cross the unit circle. And bam, there's going to be a jump, and so on and so forth. So these are, this is what happens when you get this large system where it doesn't diagonalize, and that's it. So I'm done. Thank you for your attention.
Thank you, Mary.
Thank you very much. That was really interesting. So please, let's open the floor for questions. Just unmute yourself and ask.
Hi, can I ask a question?
Absolutely.
Thank you very much. Thank you. It was very interesting. Question is, did you try it for any other multi-step methods, or does it work for a particular one?
Oh, so everything we did generalizes completely. So we just happened, well, okay, so so there are two things. So for a multi-step method, whatever the multi-step method is, okay, so here's a generic multi-step method. The multi-step method, because the right-hand side is handled in this monolithic manner, so you have, this is the ODE that you're solving, and the multi-step method just uses that vector field evaluated at different solution values. This is going to the linearization will diagonalize. Well, linearization is either going to diagonalize or it's going to go to Jordan blocks. And so it's going to be fairly simple to analyze. It's the multi-step method where it's a semi-implicit method where you have, where you've broken the right-hand side into two pieces and you get two Jacobians. This is where we found that things can get interesting, but there's nothing, the approach will work for any time stepper you want to use. We just happen to have used this second order semi-implicit method when we were doing the PNP FBV systems. We chose to use this time stepper, but everything we did could have been done easily with any other time stepper. The adaptive time stepper can be built for any other time stepper. The linear stability analysis can be done for any other time stepper. And this thing about the adaptive time stepper finding the threshold, that can be done, that will happen for any time stepping method that is conditionally stable. So it's not specific to SBDF2. Whatever method you wanted, this approach and this machinery could be used.
That sounds fantastic. Dr. Pugh, very quickly, I'm sorry for everybody, just very quickly, just to clarify, this dangerous jump out of the stability sort of, or is a jump out of stability, that strange jump we were observing on the graph,
yes.
that it's happening before we sort of converge to the lowest possible, value of step. or not lowest possible, but to the lowest error possible, you know, so, which sounds reasonable. So do I understand correctly that while we are trying to find that reasonable step, so not to spend too much time and at the same time have the lowest area, we have a danger zone?
Well, so, okay. So hi, Marina, it's so nice that you're there. So, so let's see if I can, so with, so let me see if I can, okay. So here was when we had the adaptive time stepper. And what happens is when the solution is, here, everything is wonderful. The solution is getting closer and closer to the steady state. And then it gets to the steady state and it takes its time steps larger and larger because that's what the adaptive time stepper is trying to tell it to do. But then it takes the time steps too large and the instability kicks in. And then it goes, oh no, I've gone unstable. It takes its time steps smaller again. And then it gets stable. And then it's like, oh, good, good. Everything's stable. Life is good. I'm going to start to grow my time steps larger. And then it grows its time steps larger. And then, oh no, I've gone unstable. And then it starts to take its time steps smaller until it's in the safety zone again. And so this is why it kind of is always staying on the razor's edge, because it's taking its time steps as large as it can because it wants the error, because of the lower bound on the local truncation error. But then if it takes its time steps too large, the system becomes unstable and the upper bound on the local truncation error kicks in and it takes its time steps small again. And so if you like zoom in on this, there you see that it's always kind of flirting with that horizontal line.
Thank you so much. And Dr. Pugh, just to clarify the situation, this is Marina Chugunova version 2. This is not the Marina Chugunova you thought. I am PhD at Waterloo. I know who you are.
Okay, so that I was wondering why you couldn't pronounce my last name. No worries. It's pronounced like it's pronounced Pugh, like something you sit on.
I'm not here.
No, exactly. Okay. Thank you for the clarification.
Thank you so much.
Are there other questions?
Yeah, do we have other questions? I was actually curious. I think you clarified this with the previous question, but I wanted to ask again exactly this slide. So the dt star and the dt infinity. Mm-hmm. You said that they're the same. Is this picture the proof, or do you have a written down proof?
Oh, there's no, I mean, there's sort of hand waving. I mean, there's a plausibility argument, but I have no rigorous proof.
It would be too messy to do this for all possible schemes or something like that.
I mean, it's an argument at the level of local. It's not even a PNP FBV argument. It's an argument with how local truncation errors are bounded.
Okay.
I've never seen this type of picture. I have never seen anywhere in the literature where you have the superposition of the dotted lines and the dashed lines. I have not seen that anywhere in the literature. And the other thing that I haven't seen in the literature is this type of jump, because what this type of jump is telling you is that for one value of the parameter, you might be able to take a large time step if you were doing a fixed time step size, but then for a slightly different value of the parameter, the exact same time step would be unstable. Mm-hmm. But I've not seen in the literature anywhere something which proves that the solid line and the circles must coincide. It's something I've observed experimentally a number of ways, and I have a heuristic hand-waving argument for why it's plausible, but I've never seen it written down.
I mean, the picture is really convincing, and if it was just, yeah, you can't do something like this by chance.
No, and we've got the similar picture for the logistic equation. I just kind of glossed over it. But there's the picture for the logistic equation.
Yeah.
One of the big problems is that adaptive time steppers are not super well understood analytically.
Mm-hmm. Thank you. Other questions?
Hello, can you hear me well?
Yeah. Hi.
Okay, I have a question. It's a very nice talk. Thank you so much. So my question is, you look at now the stability region you have for the one steady state. If the equations have a multi-stability, do this numerical scheme works well either? Do you have successful examples? Thank you.
So I do not. I have not done this exercise with something which has multiple steady states, multiple stable steady states. I should, and I haven't. But what I would expect is that for each of the steady states, I could have different stability thresholds, because the stability threshold has to do with the Jacobians for a specific steady state. And so 2 different stable steady states, I'm going to get 2 different sets of Jacobians, I'm going to get 2 different sets of eigenvalues and eigenvectors, and I'm going to get 2 different busy complicated pictures like these, and I might get 1 time step constraint for one steady state and a different time step constraint for the other steady state, and which one kicks into action would depend on the initial data. Is the initial data headed towards stable steady state A or stable steady state B? And so if the initial data is headed towards stable steady state A, which has a stability threshold of dt star equals something or another, then the adaptive time stepper will equilibrate at that stability constraint. If the initial data has me headed towards the other steady state, which is going to have its own stability threshold, then the adaptive time stepper would find that stability threshold. But I haven't actually done the computation because I was just so busy with the PNP-FPV system. But if you have any system with 2 asymptotically stable steady states, it would be a really lovely experiment.
You might even get complicated like Mandelbrot sets, like you do when you're iterating just Newton's scheme to find roots on z squared plus 1 equals to 0. You get these complicated basins of attraction that intermingle and form these fractal sets. I would expect that that could be a possibility here as well.
This really sounds like something worth playing around with.
Yeah.
Unfortunately, so much of this is like numerical experimentation. It's without a theorem, some people just aren't interested. But it's really hard even to find theorems about the spectral radius of something. You have a non-self-adjoint operator. How its spectral radius depends on a parameter. Even finding theorems about that is hard.
Actually, the Wilson-Cohen system would probably be interesting because it has multiple steady states, like multiple stable states, I mean. So this would be interesting to experiment with that as well.
Does it have, so one of the reasons this was interesting is the entire reason I needed to do the semi-implicit time stepper is I have a diffusion and I have, so that's supposed to be diffusion, and I have nonlinear. And so this is why I had to use a semi-implicit time stepper and why I get these very interesting dynamics. If I had less interesting PDE or system of ODEs, then I might just use something like a multi-step method where I don't think it would be quite so interesting at the numerical analysis level. But yeah, I mean, it would be fun to play around with other systems.
Thank you.
Okay, if there are no more other questions, then I would like to thank you again for this wonderful talk. I'll stop the recording, and people can either